You're looking at the very first image captured by the largest digital camera ever built for astronomy, now installed at the heart of the Vera C. Rubin Observatory in Chile. This breathtaking view reveals the southern portion of the Virgo cluster, located about 55 million light-years away. It's the closest large gathering of galaxies to our own Milky Way, and Rubin brings it to life in extraordinary detail. The image showcases a stunning diversity of cosmic objects, brilliant stars in hues from blue to red, nearby spiral galaxies glowing in icy blues, and distant galaxy groups painted in deep reds. Altogether, the full image contains more than 10 million galaxies, and it was assembled in just 7 nights, using nearly 1,200 individual exposures. No other telescope in the world can match Rubin's ability to capture such a wide and deep image of the universe in so little time. But this is just the beginning. The Vera C. Rubin Observatory is unlike anything we've built before. Equipped with a 3.2 gigapixel camera, the largest digital camera ever put in space or on the ground, it will scan the entire southern sky every 3 nights for the next 10 years. That's around 20 terabytes of data per night, leading to the most detailed time-lapse movie of the universe ever created. Rubin will detect asteroids, dark matter effects, and even transient phenomena we've never seen before. With over 37 billion stars and galaxies expected in its final catalog, it's poised to rewrite our understanding of the cosmos. But how is the Rubin Observatory different from every other telescope we've ever built? For centuries, astronomers have studied the universe through still images, snapshots that freeze celestial objects in time. These images have revealed much about the cosmos, but they've also missed a crucial aspect: motion. Many cosmic events are dynamic, unfolding over seconds, days, or even years. Capturing those changes requires a new kind of observatory, one designed not to take still photos, but to record a full-length movie of the sky. That's exactly what the Vera C. Rubin Observatory is built to do. It marks a revolutionary shift from static observation to continuous monitoring. By surveying the entire visible sky every few nights, Rubin will provide a dynamic view of the universe, allowing scientists to track changes as they happen and rewind to see how they began. It's like installing a dash cam in space, one that records the cosmos in real time. At the heart of the Vera Rubin Observatory lies the LSST camera, a marvel of science and engineering. It's roughly the size of a small car, weighs around 3,000 kilograms or 6,600 pounds. The camera boasts a staggering 3.2 gigapixels. To put that into perspective, it would take about 1,500 high-definition TV screens tiled together to display one image in full resolution. The focal plane is tiled with 189 CCD sensors, each with a 4K by 4K resolution, cooled to approximately -100 degrees Celsius or -148 degrees Fahrenheit to minimize noise. Its primary mirror is 8.4 meters across, or about 28 feet, which gives it tremendous light-gathering power, similar to that of other large observatories. This arrangement gives Rubin an extremely wide field of view of 3.5 degrees across, 40 times larger than the full moon in one exposure. Here's how it works in simple terms. Every night, the Rubin Observatory will capture fresh images of the sky. Over time, astronomers will stack and combine past images of the same region to create a template image, a kind of reference picture that shows what the area normally looks like. When a new image is taken, the observatory subtracts the template from it, pixel by pixel. This process, known as difference imaging, removes everything that hasn't changed, leaving behind only what's new, moving, or variable. It's an incredibly powerful technique. Whether it's a brilliant supernova suddenly flaring up, an asteroid zipping across the sky, or a star pulsating in brightness, Rubin will detect about 10 million changing objects every single night. What's truly remarkable is how fast all this will happen. Rubin will observe a patch of the sky for 30 seconds, capturing a deep, high-resolution image. Then, within just 5 seconds, the 600-ton telescope will turn to a new patch and begin the next exposure. Each 30-second exposure will generate a massive 3.2 gigapixel image that will be read out in just 2 seconds, keeping the cycle moving seamlessly. This rapid rhythm will repeat all night long, allowing Rubin to scan huge portions of the sky with astonishing speed and precision. In just 3 nights, it will have imaged the entire visible southern sky, capturing anything that hasn't changed, moved, brightened, or suddenly appeared. And with this relentless observing comes a tsunami of data. Every 24 hours, Rubin will generate about 20 terabytes of raw image data. Over its planned 10-year mission, the observatory is expected to collect over 5 million individual exposures, adding up to roughly 60 petabytes of data. To put that into perspective, that's 500 times more data than the Hubble Space Telescope has gathered in its entire 35 years of operation, significantly more than all the ground-based telescopes in history, and about 1 million times more than the entire English-language Wikipedia. To grasp just how massive Rubin's data flow will be, let's compare it with the 2 most famous space telescopes. Hubble collects about 8 terabytes of raw data per year, while the more advanced James Webb Space Telescope gathers around 200 terabytes annually. Rubin, in contrast, will produce a staggering 20 terabytes every single night. In just one night, Rubin will collect more than twice as much data as Hubble does in an entire year. This staggering scale isn't just a leap, it's a data revolution, one that will reshape how astronomy is done in the 21st century. The Rubin Observatory is built to uncover what we've been missing: faint galaxies, transient events, mysterious objects that have always been there but just out of view. And it got me thinking, what else are we missing? Not in the sky, but here on Earth in our everyday lives. It turns out the same problem exists with our news. Most of us only see a narrow slice of reality, shaped by the outlets we follow, the region we live in, or the algorithm that feeds us headlines. And when it comes to science news, it gets even trickier. Headlines are often exaggerated or oversimplified to get clicks. That's why I use Ground News. It's a platform that helps you cut through bias and hype by comparing how different media outlets are covering the same story. It shows you political slant, headline framing, and even what stories you might be missing entirely. For example, when the first images from the Vera C. Rubin Observatory were released, I wanted to make sure I was reading unbiased, credible coverage. Ground News made that easy. This story was covered by 197 news sources, and with Ground News, I could instantly see that the bias distribution was almost equal. I could even check the factuality ratings of each outlet, verified by 3 independent media monitoring organizations. And here's something cool. The founder of Ground News is a former NASA engineer, so you'll find a strong foundation for trustworthy science coverage too. My favorite feature? The blind spot. It highlights stories that are disproportionately covered by one side of the political spectrum, so you're always aware of what your feed might be leaving out. If you're only interested in topics like science, technology, or space, there's even a feature called Interest Pages that filters the noise and shows you only what matters to you. And for viewers of this channel, there's a special offer. For a limited time, you can subscribe and get 40% off the Unlimited Access Vantage plan by scanning this QR code on screen or heading to ground.news/SOU. The link is also in the description. The first image released by the Rubin Observatory is nothing short of breathtaking. This standout image spans an astonishing 14 square degrees of sky, about 70 times the area of the full moon, and was built from more than 3 trillion pixels of data gathered over just 7 nights. Let's take a closer look at what this cosmic masterpiece reveals. Zooming in on this patch, we see a giant elliptical galaxy, M49. It glows with a soft yellow halo and is home to older stars. These ancient stars give it a reddish tint, suggesting that star formation has long since slowed or stopped. To the left, we find NGC 4535, a spectacular face-on spiral galaxy. It sparkles with brilliant blue and white light, a signature of active star formation. Its beautifully defined arms are rich with gas and dust, where clusters of hot, young stars are lighting up the galaxy in stunning hues. Between these two giants lies a diverse zoo of other galaxies, a notable 2-armed spiral, massive ellipticals, and faint dwarf galaxies. And in the background, layered across the image like scattered rubies, are the reddish smudges of galaxies even farther away, some more than 1 billion light-years away. As we leave behind M49 and its galactic neighbors, we arrive at one of the largest and most striking spiral galaxies in the Virgo cluster, Messier 61. This grand design spiral galaxy offers a rare face-on view of what galaxies like our own Milky Way might look like from afar. Discovered nearly 250 years ago, M61 has since become a favorite target for astronomers, including detailed observations by the Hubble Space Telescope. At its center lies a supermassive black hole, weighing about 5 million times the mass of our Sun. But what truly sets M61 apart is its vibrant activity. It's classified as a starburst galaxy, meaning it's undergoing an unusually high rate of star formation. This is clearly visible in its brilliant blue arms, glowing with the light of countless hot, young stars. M61 isn't just beautiful, it's a snapshot of a galaxy in its prime. Now we arrive at one of the most thrilling sights in the entire image, a galaxy triple merger. This chaotic and rare scene captures 3 galaxies in the midst of a cosmic collision, their shapes warped and stretched by mutual gravitational forces. As these galaxies interact, their stars and gas are pulled into dramatic tails, bridges, and arcs, creating a stunning display of motion frozen in time. You can still trace the spiral patterns of the original galaxies, but they appear twisted and distorted, a clear sign that these systems are being reshaped by each other's gravity. Mergers like this are more than just beautiful, they're transformative. They can trigger bursts of star formation, fuel supermassive black holes, and eventually give rise to entirely new kinds of galaxies. Just south of the merging trio, we find a more peaceful scene, 2 stunning face-on spiral galaxies. At first glance, they seem close enough to be dancing partners, but looks can be deceiving. These galaxies are actually far enough apart that they can coexist without disturbing each other. The galaxy on the right is about 20 million light-years farther away than the one on the left. That's enough distance for them to coexist without gravitationally disturbing each other. No merger here, just 2 elegant spirals quietly spinning in the vastness of space. Just below the merging galaxies lies a subtle but extraordinary sight, a cluster of faint reddish smudges. This is a cluster of distant galaxies bound together by gravity, far beyond the Virgo cluster. Their orange-red glow is a telltale sign of their immense distance to Earth. This image isn't just a window into distant galaxies. Scattered across the entire image are extremely bright objects with spikes, such as this one. These are stars in our own Milky Way, shining millions of times closer than the faint galaxies in the background. The dramatic diffraction spikes you see aren't part of the stars themselves. They're a result of how light interacts with the telescope's structure. As we zoom out, you might notice the sawtoothed, jagged edges of the image. That's not a glitch. These uneven borders mark the areas that Rubin has yet to fully capture. This is the annotated version of the full image. In the top left, you can spot the region where we saw those three galaxies locked in a cosmic merger, one of the most dramatic highlights of the scene. But here's what makes this image truly remarkable. Most of the objects aren't labeled because they've never been studied before. Many of them have never even been seen until now. Thanks to the unparalleled depth and scale of Rubin's observations, countless galaxies and cosmic structures are coming into view for the very first time, waiting to be explored. Galaxies and stars weren't the only things that made this image exciting. There's something else hidden in plain sight. You can't see it immediately, but it's scattered all over the image. Let's zoom in on this section. This part of the picture has been photobombed by asteroids, and you can spot them as colored streaks crossing the image. These streaks trace the paths of asteroids moving through our solar system during Rubin's long exposures. While they're just passing through, Rubin is smart enough to detect and remove them from the final stacked image, ensuring a clean view of the distant universe. Here are a few clips of asteroids discovered by the Vera Rubin Observatory. And remarkably, we're seeing these space rocks for the very first time. In just 10 hours of observations, Rubin detected nearly 2,100 new asteroids zipping through our solar system. To put that into perspective, all other ground and space-based observatories combined typically discover around 20,000 asteroids in a full year. As of today, astronomers have identified about 1 million asteroids in our solar system, but Rubin is poised to multiply that number fivefold. Within just a few years, it's expected to push the count to 5 million, revolutionizing our understanding of the small bodies that orbit our Sun. Another breathtaking image released by the Vera C. Rubin Observatory captures a vibrant, star-forming region featuring two iconic nebulae, the Trifid Nebula and the Lagoon Nebula. At the center of the image, you'll notice a glowing pink kidney bean-shaped cloud. That's the Lagoon Nebula, a massive stellar nursery located about 4,000 light-years away in the constellation Sagittarius. It's so bright that you can spot it with just a pair of binoculars or a small telescope. Above it lies the Trifid Nebula, roughly 5,000 light-years away, and packed with dramatic contrast and color. What makes the Trifid so striking is the mix of features it packs into a single view. A pink emission nebula, a cool blue reflection nebula, and dark dust lanes that divide it into three distinct lobes. Hence the name Trifid. Inside, new stars are actively forming, releasing powerful winds and radiation that sculpt the gas around them. It offers a vivid glimpse into how massive stars shape and reshape their surroundings, even as they're being born. Together, the Trifid and Lagoon Nebulae provide an extraordinary window into the earliest stages of star formation, revealing how giant clouds collapse, how clusters of stars come together, and how newborn stars begin to transform their cosmic cradle. The Vera C. Rubin Observatory has been built to answer some of the biggest unanswered questions in astronomy and physics. It will empower astronomers to explore the universe across four major scientific frontiers. The first, and perhaps the most exciting, is mapping the transient sky. In astronomy, transient events are celestial phenomena that appear for a relatively short period, changing in brightness or position before fading away. This includes supernovae, gamma-ray bursts, fast radio bursts, or flaring black holes. Because Rubin will scan the entire sky every few nights, it's uniquely positioned to catch these explosions shortly after they begin. It's expected to detect around 100,000 supernovae each year, from relatively nearby ones to those occurring billions of light years away in the early universe. This fire hose of supernova data is a goldmine for astronomers. Why? That's because certain types of supernovae are used as standard candles to measure vast cosmic distances and track how fast the universe is expanding. In fact, it was through supernova observations that scientists discovered the universe's expansion is accelerating, a breakthrough that led to the theory of dark energy. Studying these supernovae will help astronomers refine the value of the Hubble constant, the critical number that tells us how fast the universe is expanding. But beyond that, Rubin's observations will also shed light on the very moment a star dies, offering a more detailed understanding of the complex physics behind stellar collapse and explosion. This groundbreaking observatory is named after Vera Cooper Rubin, the pioneering astronomer who provided the first strong evidence for the existence of dark matter. In the 1970s, Rubin's meticulous work tracking the rotation speeds of galaxies revealed something extraordinary. The stars were moving far too fast to be held together by visible matter alone. Her discovery showed that some unseen mass, what we now call dark matter, must be shaping galaxies from behind the scenes. Today, the Rubin Observatory continues her legacy on a cosmic scale. One of its central missions is to solve the mystery of dark matter and dark energy, the invisible forces that govern the universe's structure and fate. Together, these dark components make up about 95% of the universe's mass energy, yet remain among the greatest enigmas in physics. Rubin will use a technique called weak gravitational lensing to map dark matter. As light from distant galaxies travels through the cosmos, it's subtly distorted by the gravity of all the matter it passes. By measuring these tiny distortions across billions of galaxies, Rubin will create a vast map showing how dark matter is distributed across space. At the same time, the observatory will help us understand how the universe has expanded over time, offering crucial new clues about dark energy, the mysterious force accelerating that expansion. The third key scientific goal is a census of the solar system. We currently know of about 1 million asteroids, primarily located in the belt between Mars and Jupiter. Rubin will likely discover several million more orbiting the Sun. It will also extend our reach to smaller objects. For example, astronomers believe there are hundreds of thousands of near-Earth asteroids, some of which could be hazardous to Earth. Rubin's survey will be so thorough that it should catalog the majority of asteroids larger than a few soccer fields in size that come near Earth's orbit, thereby helping assess any future impact risks. It's like doing a 10-year safety sweep of the cosmic neighborhood. But these discoveries won't be limited to the asteroid belt. Rubin is expected to find thousands of new icy objects in the Kuiper belt. Until recently, astronomers had discovered only a handful of these so-called trans-Neptunian objects. Today, we know of a few thousand, but the Rubin Observatory is poised to change that picture entirely. With its powerful wide-field survey, Rubin could discover tens of thousands of new Kuiper belt objects, dramatically expanding our catalog of icy worlds in the outer solar system. And then there's the mystery of Planet 9. Some astronomers believe the strange orbits of a few far-flung objects point to the gravitational influence of a yet undiscovered giant planet lurking in the dark. If it exists, Rubin may not see Planet 9 directly, but it could uncover new evidence of its presence by tracking the orbits of the most distant objects in the Kuiper Belt. Finally, the Rubin Observatory will help unravel the history of our home galaxy, the Milky Way. By surveying billions of stars, including faint ones in the galaxy's distant halo, Rubin will essentially conduct archaeological research on a cosmic scale. One of its key tasks will be to identify stellar streams, long, faint trails of stars left behind by smaller galaxies that were pulled apart by the Milky Way's gravity. These streams serve as fossil records, offering clues about ancient galactic mergers and the Milky Way's dynamic evolution. Rubin's arrival couldn't be more timely. It picks up where the European Space Agency's Gaia mission left off. Gaia, which recently concluded its survey after 11 years, delivered the most precise 3D map of the Milky Way ever created, based on 3 trillion measurements of nearly 2 billion objects. Now, Rubin will build on that legacy, extending our reach deeper into the galaxy's outskirts and enriching our understanding of how the Milky Way was assembled, star by star, over billions of years. So thanks for watching, and thanks to Ground News for sponsoring this video. If you're tired of clickbait headlines and just want the real story, especially in science, scan this QR code or head to the link ground.news/SOU given in the description. You'll get 40% off the Vantage plan and finally see the news like you see the universe, clearly.